Do a quick sound check real quick. James, can you confirm that you can hear me okay?
Yeah, that sounds great, TJ. Thank you.
Okay, we can get started. On your mark, James.
Please go ahead.
Okay, great. Thanks, James. Well, hello, everyone. My name is TJ Sego. I am assistant professor of medicine at the University of Florida. I've been working on Compucell for since 2019. And the topic of our module today is one that's very near and dear to my heart, and one that I've worked on and off for the past couple of years. And this is actually the first time that this has ever been covered in a Compucell workshop. So it's especially exciting in that regard. It also comes with a certain caveat of that this is very new material. And so we will be doing some interactive work together. And the intent is to work through a very simple example that's manageable, that we can all get through and try to develop a sense of the new content that's discussed in this module, which is the CC3D Python API. And so to give you a sense of how we're going to spend our time here in the next hour or so. So I first want to try to motivate why one might want to work in pure Python, do Python scripting and more of software development type work for simulation building as opposed to working in Player and Twedit. Excuse me. And then I try to get a sense of what all can be done with Compucell, working through the new features in the Python API. And then we will dive into the code and actually do some simulation building. We're going to set Player and Twedit aside for the next hour or so. Instead, we're going to work in a Jupyter notebook. We're going to build a complete simulation, all in a Jupyter notebook, all in Python, and even set up some of our own visualization and interactive simulation control. As always, questions through the chat, and we have lots of people here to help handle questions. Otherwise, let's go ahead and get started. So as probably you're aware of by now, a lot can be done with the graphical user interfaces that are distributed with Compucell, in particular here for interactive simulation, execution and visualization in Player. But there are a lot of things that one might want to do with a Compucell simulation besides just interactive execution as you've been doing in Player, that are not so straightforward to accomplish, if not impossible. And just to give you a sense of some of the things that say we've done, those of us who use Compucell regularly in our research. So these figures here on the right, these are two examples of use cases that I've put together using these features that we're going to survey today, to do things that in Player would take a really long time to do, if doing so manually by say launching simulations over and over and over while babysitting a graphical user interface. So as an example here in the top right, so this is one big parameter sweep from a paper that we developed in 2020 in PLOS Computational Biology. Excuse me, sorry. And what's demonstrated here, as far as the actual biological relevance, is mostly unimportant to our discussion here for now. Suffice it to say that each of the subplots in this grid is one parameter set of a parameter sweep. So we have one parameter that's being varied horizontally and another that's being varied vertically. And then in each of these subplots, as you can see down here, there are multiple trajectories being plotted. Again, what's actually shown here is unimportant for our discussion today. What's important to note is that each of these subplots shows 10 different simulation replicates. And so this is hundreds of simulations. And not just hundreds of simulations, but with individual parameter sets, this doing manually would take days. Whereas this was coded up through the Python API in maybe 15 or 20 minutes, sent to a supercomputer, and was done by the end of the day. Another example here is shown here in the bottom right. This is very new. This is actually unpublished research, but this is using Compucell as the execution backend of something like a parameter fitting and sensitivity analysis routine. So this is actually doing a model of single cell migration. These are 3 different instances shown here at different time points. So the cell was here, and then here, 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 and here. And the problem statement here was find a chemotaxis parameter that would bring this cell from this dashed line to that one over a certain amount of time. And then for a given temperature or fluctuation amplitude, what is that optimal parameter as a function of the fluctuation amplitude? All of this is done by integrating Compucell with this. I did this with SciPy. But by and large, most of this is really routine, say like something like curve fitting or optimization problems and sensitivity analysis. These are typically done with something like analytic functions, but it's certainly possible to do these same sorts of workflows where the actual target model is a Compucell model. All of this is done in the Python API. And if that's at all intimidating or overwhelming to you at a glance, I just want to point out that you have already been working with one of the main features of the Python API throughout the week so far, and that is the steppable. So your Python steppables that you've been writing to either implement custom models or perform specific visualization or data analytics routines. This is just one part of the Python API. So you're actually part of the way into this feature set already just by virtue of doing, I guess, what we I think of as more like classic Compucell development. Python steppables are custom user code specified in Python. And what we will get into is the rest of the feature set, or at least a major part of it, to show what all else you can do in Python with Compucell outside of a graphical user interface. Now, the main goal here for this feature set is to be able to use Compucell as a software library. Using Compucell in the graphical user interfaces that you've been using is one approach to use Compucell. But for all sorts of other applications, whether it's integration and optimization workflows, or say coupling Compucell simulations with either other simulators or with things like, say, machine learning algorithms, everything else requires using Compucell as an integrated software library, and the Python API delivers that functionality. But it's important to note that all of the backend features, all of the computations, all of the models, everything is the same. Everything that you've learned to date, specifying your simulations in CC3D ML with some Python steppables, everything is the same. This is just a different user front end. So instead of using a mixture of CC3D ML and Python scripts that are executed in player, instead, everything is specified in something like a Python script or a Jupyter notebook, and you have all of the capability to make those specifications and then orchestrate your simulation just all yourself in Python scripting. And so in that regard, most of the procedures are the same as what's already done by player for you, which is to take a specification, say, create a simulation, add some plugins or steppables to that simulation, perform some startup routines like calling your steppable start method, do some stepping to integrate through the simulation, and then do some finalization. This is mostly automated for you by player. Having full control over these procedures in Python gives you a lot of opportunities to interconnect your simulation with other stuff. For example, to pull, say, model parameters from some external algorithm, say something like an optimizer, where an optimizer chooses new model parameters for you. Doing this in the Python API is really straightforward. There is a lot of, say, startup routines that one might want to do when setting up their simulation, like, say, reproducing a visualization configuration that you've, say, produced at some previous time. And then a lot of additional things that one can do while actually integrating a simulation. And a really simple example to just check some external termination condition to decide when you've, say, stepped your simulation for long enough. But of course, also connecting, say, simulation data to external algorithms like an optimizer for informing, say, future selection of model parameters. And so that very brief introduction out of the way, what I'd like to do is just dive right into it and get into the guts of this a little bit and learn by doing. And so to do this, we did a session last week on getting into the Python API very briefly, specifically on being able to launch a Jupyter notebook. And that's our jumping off point here. So regardless of operating system, our starting point is to open a terminal, or in Windows, it's a command prompt. For me, when I do this on Windows, I get something like what you see here. If you want to follow along and code all of this up along with me, then this is the place to start. And how one opens or launches Jupyter Notebook varies a little bit based on how you installed Compucell. And this is written out explicitly here in each box here at the top of the screen for your reference. If you installed Compucell directly from Conda, your launching point will be a little bit different from those of you who used the CC3D installer. Most importantly, our first step is to do what is called activate the conda environment for Compucell. And if you installed Compucell directly from conda, then your first step is really straightforward. All you have to do, again, for those of you who installed directly through conda, is to just activate the environment that you installed Compucell into. So for example, on my machine, one of my environments that has Compucell installed is called Compucell3D. And so I just type conda activate Compucell3D. Again, for those of you who installed Compucell directly from conda, now, for those of you who used the Compucell installer, your first command is a little bit longer, but it's still not too bad. So your first step is to locate the path to your Compucell installation. For your reference, this is the code blocks here on the right, and I have this noted in brackets as CC3D path. Whatever is the absolute path to your Compucell installation, you would replace what's in these brackets and the brackets with that path. And assuming you know the CC3D path, the path to your installation, if you are on Windows, in your command prompt, you will type call and then the path to your CC3D installation. And then slash mini conda3 slash conda bin slash activate. To find the path to your CC3D installation, your best bet is probably to go look in your file explorer.
All right,
The-
TJ, could you make your command prompt a little bigger? People are having trouble seeing the text.
Yeah, yes, I can. To get back to Kimberly's question in the chat, so the default location for installing Compucell will be in the root directory of your primary drive in a folder called Compucell3D. If you chose to install it in a custom location, then it's wherever you chose. But typically, if you open a file explorer and go to your root directory, if you didn't customize anything about the installation, then it'll be in the Compucell3D directory. All right, let's see, there's some comments about paths being different for Mac, which is not entirely surprising. Some of these details can vary a little bit. They probably for Mac or Linux users who are getting an issue with this path not existing, try replacing conda-bin with just bin, bin. Liam's question about the path to activating conda, that should work exactly as typed if that's where Compucell is installed. But just to be clear, so I see more issues about this issue with the path for Mac. Um, the path that should be entered should begin with the the path to the root directory of your Compucell installation. Henry also made a good suggestion that you may also just need to remove the .sh file extension. Again, some of this is expected. There's a little bit of variability on some of these details, so if it doesn't work at first, you can definitely get it figured out, that's for sure. Okay, I'm gonna rely on my supporting TAs to try to work through some of these details, but please someone stop me if there's some catastrophic issue that needs to be addressed. For anyone who falls behind for whatever reason, no worries, all of the slides will be available. And having accomplished this step, once the Conda environment is activated, the next step is to launch Jupyter Notebook. That's what we're going to be doing all of our coding today. And you can launch Jupyter Notebook by just typing exactly what's here in the middle of the screen, just all lowercase Jupyter Notebook. So type that and press return, and what you should find is something like, say what you see here is an example on my screen. This is just one of the many locations that I have a bunch of Jupyter notebooks, all sorts of various projects. You should see a browser open up that looks something like this. And what we will do is in the top right, press new and then notebook. That'll create a new Jupyter notebook. And we'll just work in that one new Jupyter notebook for this module. So again, after activating the Conda environment, you type Jupyter notebook. And once you are here, something like a brand new notebook, can start by testing to make sure everything works and you have access to Compucell in Python. You can do this by just typing import CC3D and execute it. And execute by in the menu bar pressing run and then run selected cell. You also have some shortcuts to do the same. What you should find is when you execute this cell that just says import CC3D, it'll do some thinking, and if you have no issues, then you should just see a bracket 1. All right, we'll give everyone 30 more seconds to get to this point. All right. Again, get with a TA, if you've got stuck on any of these particular details, and again, all of the slides will be shared with step-by-step instructions on how to complete all of these steps. If you're with me, then you can just delete this first test cell. Should start you back at a blank Jupyter notebook cell. And I'm going to split my screen here and we're gonna just get right to it. So the Compucell simulation in the Python API, as you know them, is executed in Player. In the Python API, they are encapsulated inside of a class called CC3D Sim Service, just short for Simulation Service. Now, when creating a CC3D Sim Service instance, you will have a Python object that contains all of the simulation stuff that Compucell does, and you can modify it, interact with it, and control it throughout your Python script. And so a good place to start here, we'll start by creating something like a skeleton using the pattern here that's shown in the bottom left of my screen. In general, when creating a Compucell simulation in the Python API, this is the procedures to follow. Though for now, neglecting the part where we actually add all of our interesting model specification. So if you're following along with me, you can get access to the CC3D Sim Service class by typing from cc3d.compucell setup .cc3d caller import CC3D Sim Service. Again, that CC3D Sim Service, that is the container class for a Compucell simulation. And we create one of these by just instantiating one of these classes.
PJ, if you're willing to cut and paste that text into the chat, that would save people a lot of typing.
I cannot. Oh, this, what I type in here, sure. Yeah, I can talk through it as I type it, and then I will copy and paste. So, having done this instantiation, this just really gives us something like a shell of a CC3D simulation. There's really nothing there at the moment. It's certainly not populated with any models. It's just more like an object that you can populate with your model for execution thereafter. And in general, the startup routines to get a Compucell simulation executable first is to call the method run. I'm going to refer to my simulation object as CC3D Sim. So you can do CC3D Sim.run. This instantiates the actual simulation in memory. Second step is to perform all initializations. This is a step that Player does for you when you start a simulation. This does all initialization routines for everything that's been added to the Compucell simulation. And then lastly, call a method start. And this one you may recognize from working with stepables. When this method start is called, every stepable that you have developed and then registered with your Compucell simulation, this call will call start on each of your stepables. In general, this set of procedures is always done when initializing a CC3D simulation in Python. I will just put a placeholder here because there's a step between the beginning and end of the code that we just wrote, and that is that between instantiating the simulation and then calling run, we'll add stuff to it. And this is the step that we will complete throughout our time together today. I'll put all of this code here in the chat. That should be copyable from the chat directly into your Jupyter notebook. Now you'll find that if you execute this cell, this will fail. I'll go ahead and try it just to demonstrate. See that there's an error that comes up here. The details here are mostly unimportant. The problem here is that nothing has actually been added to the Compucell simulation. And so when you try to instantiate it in memory by calling run, CC3D Sim Service rejects it, saying this is an empty simulation. There's nothing here to do. So instead you get an error. All right, so much of the rest of our task for today all involves populating this placeholder here, just adding model specifications to this CC3D Sim Service instance. Now, the important thing to reiterate from some of our previous discussion is that everything that is in the CC3D ML that you've been working with throughout the week already, everything you've already learned, there is an analogous way to specify those things through the Python API. The volume plugin, cell type plugin, diffusion solvers, any custom steppables, all of those things are all available through the Python API. And to the extent that it's possible, there's a one-to-one correspondence between the specifications that you've already learned in CC3D ML, shown here on the right for the POTS element. You learn how to specify dimensions and steps and the neighbor order for the POTS element. There is a corresponding specification object in Python that takes the same information inputs, sometimes with slightly different names, and they specify the exact same thing. And we can get a feel for this again by doing working together through some examples here. So let me clear this error because I find it distracting. Just going to go and restart my kernel. And okay. In general, all of the Python API objects for specifying model and simulation stuff is defined in a Python module within Compucell called PyCore specs, which is short for Python core specifications. And we can just get right into it here a little bit. Let's just get right into it. So what we will do generally is create different PyCore specs objects. Each of these objects corresponds to a CC3D ML element as you've learned them so far. And CC3D Sim Service will know how to interpret all of that information in the same way as if it were specified in the CC3D ML. And we can start off with an example by specifying a POTS element. We can get each of these PyCore specs objects for defining various CC3D ML elements from PyCore specs module, which you can get from cc3d.core.pycore specs. So from cc3d.core.pycore specs, we will import a class called POTS core. POTS core corresponds to the POTS element of CC3D ML. And to actually create one of these instances to give to the CC3D Sim service, we instantiate it. And let's assign this to a variable called POTS_specs. pot specs equals pots 4. And we can start some parentheses. And we will define a 2-dimensional simulation where the dimensions of the simulation domain are 100 by 100. As I said, there's a one-to-one mapping between the information contained in these different PyCore specs objects and their corresponding CC3D ML element. For pots, there is the dimensions for the Python API. These are specified through the keyword arguments dim_x. We're specifying the dimension along the x direction. dim_x equals 100. dim_y equals 100. It's the dimensions along the y direction. We can also specify the neighbor order with the keyword argument on neighbor_order. And we're going to build a simulation that has periodic boundary conditions. We can specify these with the keyword arguments boundary_x or y or z with their corresponding dimension. And we'll say boundary_x equals periodic and boundary_y equals periodic. There are a lot of other options that one can specify for this POTS core object. There are lots of, every keyword argument has a default value. And these mostly follow defaults in the CC3D ML as well. We can continue by also adding a couple of cell types to our simulation. We're going to do a 2D simulation with periodic boundary conditions, and we're going to work with 2 cell types, and we're essentially going to make them move in a very, very simple way. And we already know that we can add cell types through the cell type plugin through CC3D ML. Going to add another cell and add a couple of cell types by using the PyCore specs class cell type plugin. Cell type plugin corresponds to the cell type plugin in CC3D ML. And you can get this class from the same location. We'll do this a lot from cc3d.core.pycore specs import cell type plugin. If you're a stickler for efficiency, you can add this to the previous import. I'm doing this more for demonstrative purposes. I acknowledge the redundancy and also generally find it annoying. And same procedure here to create a cell type plugin instance. We will also instantiate this. We're going to create 2 cell types. We'll call them type 1 and type 2. I'm going to keep a little bit of generality because we'll refer to some of this information a little bit later. So let's first start by instantiating a list of strings called cell_types. And we'll just make a list of the name of each of our cell types, type 1 and type 2. And then let's actually create an instance of the cell type plugin. We'll assign this to a variable. If you're following along closely with me, I'm going to call it cell type specs equals cell type plugin and just pass the list, unpacking it. So asterisk the cell types, just the list we just defined. And that's it for the cell type plugin. This is the same as creating a cell type plugin instant or element in the CC3D ML and just listing all of the names of cell types that you want to add to your simulation. We'll continue and power through a few more and then actually load all of this information in and get a CC3D simulation running in a Jupyter notebook. By now, you're probably aware that most of the time you'll need a volume constraint or something similar to make your cells actually stick around for longer than a couple of simulation steps. We're going to use a volume plugin. Volume plugin is retrieved from the same location from cc3d.core.py core specs import volume plugin. And for this example, we will assign a target volume of 25 with the lambda parameter of 2, and we will assign that to both of our cell types. We're going to get a little bit Pythonic here and exercise some of the Pythonic aspects of the API. Let's first start by just generically declaring variables for our target volume, again, equal to 25, and our volume parameter, call it lambda volume equals 2. And this time we'll first start by just instantiating the volume plugin. Volume underscore specs equals volume plugin. And in this case, we'll assign a target volume with this lambda parameter to each of our two cell types, and we'll do so in a loop. Now, each of the PyCore specs objects has all sorts of features to try to streamline and make, say, putting all of this information together as intuitive as possible. And one example of that is to iterate over all of the cell types that are defined in the cell type plugin. And you can iterate over every one of those cell types using the attribute cell types on cell type specs as follows: for cell underscore type in cell type specs is our cell type plugin instance dot cell types. So iterate over every cell type that's registered in the cell type plugin. This will iterate again over every type specified in the cell type plugin, with the caveat of that the medium always exists regardless of whether you specified it. So in iterating over cell types, you should find that you will get values for every cell type prescribed here and the medium, because the medium always exists in Compucell. And we can't assign a volume constraint to the medium, so we want to catch this case and say if cell type not equals medium. So every cell type in the cell type specs instance that's not the medium, we're going to add a volume constraint to each, or to the volume plugin for each of our cell types. We can do so as follows. So volume underscore specs, our volume plugin instance. This has a method called param, which is short for parameter, underscore new. Create a new parameter. And we first provide the cell type that we're adding a volume constraint to. And we can use the keyword argument target underscore volume equals our target volume. This prescribes the target volume for the cell type that we're adding. And then secondly, the parameter value, keyword argument conveniently is lambda volume. The volume specs.param new, we provide the cell type that we're adding a constraint to, the target volume, and the model parameter. Give everyone 10 more seconds. All right, just a couple more to power through. Next, let's add a contact plugin instance. Contact plugin is found in the same place from cc3d.core.py specs and import contact plugin.
So TJ, could I do from cc3d.core.pycore specs import star,
Yes,
and then I wouldn't have to type all of these one by one?
correct.
Okay, thank you.
Yep, it's a good question, James. And again, those of you who are particularly annoyed by redundancy, instead of doing each of these one by one commands of importing each individual class, you can instead just one time have a star there. All of these will be available. This is another point of redundancy that's more to help make the connection between what we're using and where it's found. Yep, good question, James. Thank you. Okay, let's add a contact plugin. So in this case, we'll just have one contact parameter that's assigned to all interfaces. We're not going to do any differential adhesion or anything to that effect. Keep things nice and simple. So let's start by declaring just a variable contact underscore energy and say that that's equal 10. And we're going to assign that to every possible contact interface. So interface between the medium and each of the cell types, and then all possible combinations of the cell types. And we can do so first by instantiating our cell type plugin. I'm going to call it contact underscore specs. And say contact plugin. I'm going to enter a 2. This first argument is the neighbor order of the contact calculations. Not providing any cell type specific information yet, just first telling the contact plugin what neighbor order to use when doing contact calculations for calculating neighborhoods. And then we'll just go one by one, very straightforward, just add contact parameters. Contact plugin also has a method param underscore new. And the specification here is very similar to the volume plugin. We first specify the 2 cell types of interest for this call. We can specify these with the keyword arguments type underscore 1 and type underscore 2. This prescribes the 2 cell types. First, specify this for the medium and the first of our 2 cell types. You can here either just explicitly write type 1, or if you like to be a little more generic in your coding, you can refer to the first element in our cell types variable that we defined previously. So we specify the 2 cell types and then just the parameter, the keyword argument energy. Energy equals contact energy. We just specified a value of 10 for all interfaces between the medium and cells of type 1. And then you can just fill this out by copying and pasting for all other possible interfaces. The medium and cells of type 2. between type 1 and type 1 cells, between type 1 and type 2 cells, between type 2 and type 2 cells. Again, this is using keyword arguments to specify the two types of cells and then the parameter for those two types. This is very similar to what was done here with the volume plugin. This is first specifying the cell type, then the target volume for that cell type using the keyword argument target volume, and then the parameter for that constraint using the keyword argument lambda underscore volume. I'll also point out that it's not necessary to, well, maybe it's simpler to say that these are symmetric calls here, and that type 1 and type 2 is essentially the same as reversing the order here. So I could say type 2 equals cell types 0 and type 1 equals cell types 1, and that would be the same thing. And again, as a reminder, when first instantiating the contact plugin, there's just this integer that's being passed here. This is the neighbor order that's used in the contact plugin's calculations. So I'm determining the neighbor order for implementing all of these contact calculations. The neighbor order is specified with this integer. So here, this is a contact plugin with the neighbor order of 2. Okay. Continuing, this is our last one, I promise, before we actually try to see if this works. Let's add some cells. Create another cell here. In this case, we're going to use a uniform initializer, and we are essentially going to just put down a sheet of cells that covers our entire simulation domain. And the uniform initializer is also available in PyCore specs from cc3d.core.pycore specs, import uniform initializer. And the uniform initializer has a couple of ways to add different regions. We're going to do this in a really straightforward way. So let's first instantiate an instance of our uniform initializer. If you're following closely with me, I'm going to call it unif for uniform, init for initializer, and then specs, and just create it. Now, the uniform initializer, just like in the CC3D ML, supports specifying multiple regions. And in the Python API, you specify a region by using the method region underscore new. And all of the requisite information in the Python API is also the same as in CC3D ML. We first specify the width of a cell. Here we're going to say width equals 5. So this will create a region with cells that are 5 voxels by 5 voxels. We specify the minimum point of our region. So we define a square by 2 points. The first point.
Sorry, people would appreciate it if you'd cut and paste the each cell's code in the chat as you complete it, so they can double check what they've got. I agree with them because I just made a typo and it scrolled off the top of the screen and I couldn't find it. So thanks very much.
Yeah, absolutely. If anything, If I have any typos in my notebook, you will have the same typos as me. We can just debug the same code together. So there's, I'll just go ahead and add in all of the cells for the PyCore specs that we've implemented so far. And if I forget, please remind me going forward. I will do so for the rest of the cells that we complete together. Okay, so defining the 2 points for a region for a uniform initializer. First point, we can use the keyword argument PT for point, and underscore min, and we just provide tuples of integers. For our first point, we'll just use the origin, 0, 0, 0. And as I said a few moments ago, I'm going to cover the entire simulation domain. So our second point, which we can specify through the keyword argument pt underscore max equals, and then another tuple, and we're going to just use the point in the simulation domain across from the origin, and rather than write this out explicitly, instead we can just reference our POTS core instance, specifically to use the dimensions that are specified for the POTS element. And we can do this using the attributes dimx and dim_y. So our POTS PyCore specs element was, if you were following along closely with me, I called it POTS underscore specs. And we'll say dot dim underscore x, POTS specs dot dim y, and then 1. We do a 1 here because a 2D simulation in Compucell is actually just a 3D simulation with only 1 voxel along the z direction. Okay, and then lastly, we provide all of the cell types to populate this region with. We do so with the keyword argument cell underscore types. And if you're following really closely with me, we can just use the variable we defined previously, which is the list of our cell type names. Cell types equals cell types. Yeah, the keyword argument is for specifying the cell types to populate the region with, and we just conveniently named our local variable the exact same. Okay, again, inheriting whatever typos I may have unintentionally put into my code. Here's a copy of what I have typed out in my notebook. If anything, will have the same bugs. Now note that you can do this call repeatedly to define multiple regions. And every time you call this, the uniform initializer will store the information that you have specified, just like in the CC3D ML. All of that information is used to populate different regions of the simulation domain with whatever information you provide per region. Okay. If you are with me, then you are ready to try this out and see how things go. So our last step here to actually get a simulation executable is to take all of the specs that we've defined so far and get them into the CC3D Sim Service. We go back to our very first cell that we developed. I will put this in the chat so that you're working from the same skeleton as me if you prefer. You want to fill out this placeholder that we put at the very beginning of developing this Jupyter notebook. Want to add model stuff to the CC3D Sim Service. We can do so with the CC3D Sim Service method register underscore specs. And all we pass here is just a list of all of the PyCore specs instances that we want to register with the CC3D Sim Service. And so we'll just fill this list out, everything that we defined so far. So if you're following really closely with me and named all of your stuff the same as my stuff, then we have the POTS instance, just POTS underscore specs, cell type plugin, which I called cell underscore type underscore specs. We have the volume plugin, which I just called volume specs. Contact plugin, which I called contact specs, and the uniform initializer, I called unif init specs. Again, that's all defined in a list. That list just gets passed to register specs on the CC3D Sim Service instance. I'll note as an aside, while those of you who are typing this out are continuing to do so, that it's possible to have multiple CC3D Sim Service instances simultaneously executing and being initialized and all of that, in which case for each CC3D Sim Service instance, you just pass whatever specs you want to register with every CC3D Sim Service instance of interest. So this is not something, I mean, this is all completely specific to the particular CC3D Sim Service instance that you are calling register specs on. All right, we're ready to test this thing out. So I think we are desperately running out of time, and I really want to at least get us to a point where we can actually get a simulation visualized in the notebook. So let's just skip the explanations for now and blindly follow along. What we will do now is get a visualization pane as you know it from Player, but situated in the Jupyter notebook. You can do so by calling the method visualize on your CC3D Sim Service instance. Grab your CC3D Sim Service instance and call the method visualize. Don't have to call anything on it, or don't have to pass anything to it. Now, all other details aside, you can test this out and see if anything shows up or if we get any errors. You can do so by going to the menu bar, clicking on Run, and then Run All Cells, and let's see what happens. Get a little bit of debugging information that will show up. That's nothing to worry about. What you should find is that I get a bit of a pause here as everything is set up and the visualization is being all put together and forwarded to the Jupyter notebook. And if you don't get any errors, then you should see something that finally looks familiar. Almost. This call to CC3D sim.visualize, my apologies. This needs to be assigned to a variable. This returns an actual object that is the visualization frame that's created. Apologies for the confusion on this. So if you're following along, you'd say frame underscore cells equals CC3D sim.visualize, and then call show on it. You don't have to re-execute the entire notebook. You can just update your cell. I will put what I have there in the chat. Call that again, and there you go. Voila. Should find that when you hover over with your mouse, you can zoom in and out. All the navigation is the same as in Player. This is all the same visualization backend. Now it's just showing up in a Jupyter notebook as opposed to in Player. Now you may be wondering, well, how do I execute this? Because it's not actually doing anything, which we would expect, and that's it's a fair thing to be curious about because by now we're used to being able to press the play button in player and suddenly the simulation starts playing. When you work in the Python API, you have control over how the simulation is executed and when it's executed. And you may have noticed that we've not told the simulation to actually do any stepping. And so in player, I'm sorry, in the Python API in general, the CC3D Sim Service instance has a method defined on it called step, and it just steps the simulation one time, including calling the step method of each of your steppables. So ordinarily, if you're working in just something like just a basic Python script, you can say something like for step in, say, range 100, and you could just say CC3D sim.step. And that will step just as you would expect when running the simulation in player. We're going to use a feature that is designed on the Python API specifically to support integration in Jupyter Notebook, which is a little bit of some interactive features built out of, well, we can get into the details here momentarily. Suffice it to say that it's possible to actually put something like the play and pause button in player in a Jupyter Notebook. If you're following along with me, first, we will import some basic Python infrastructure to display additional widgets, and that is through a module IPython. So you don't need to know what this is. All you need to know is that if you type this and follow along, that you should get the same outcome as what you see on my screen. So if you type from ipython.display, import display. Those of you who work with Python development regularly, you may recognize this. This is the typical way to display widgets in a Jupyter Notebook as provided by IPyWidgets, which is what some of these features are built on. You don't know what any of that means, that's okay. If you don't care at all, that's totally fair. From ipython.display, import display, and we're going to call this display method that we just imported, and we're going to call that on something that's returned by the CC3D Sim Service instance method Jupyter _run _button. Display CC3D sim.Jupyter run button. I will put this in the chat. And I think we may be out of time. So, again, you don't have to restart the notebook. Instead, you can just execute that cell again. And you should find when you go down below the graphics for the CC3D simulation, now there's a button here that shows up called Run Simulation. And when you click that, there goes the CC3D simulation. This is analogous to resuming and pausing a simulation in player. When you click it again, it pauses. James and Hayden, how are we doing on time? Because everything I have from this point on is all on building out additional interactivity. It's not critical to being able to use this functionality, but I do think that it is insightful and also important for getting a sense of what all can be done using the Python API.
You have another 20 minutes.
Great. Like that's just about exactly the amount of time we need. So excellent. Okay, so you should have something like what you see on my screen. And so let's go back we're gonna bring our attention back to this visualize call. Visualize returns something that gives you control over the visualization frame that's created when visualize is called. As demonstrated here, for example, to show the frame. If we didn't call this show method on frame cells, then the frame won't actually show up. So you have control over when the visualization frame is actually visualized. And there are a lot of features defined on this frame object that's returned for doing all sorts of customization, specification for various visualization details, and then of course actually telling the Jupyter notebook or also in a Python script when to actually show a visualization frame. For example, this frame by default will take up the entire width of the Jupyter notebook. You have control over that through a property on that frame object called window width %. If you say 0.25 frame underscore cells dot window width % equals 0.25, you add this to your code and then re-execute the cell, you should find that now it takes up much less space. Now we will only scratch the surface of all of the stuff that's available for customizing and controlling visualization. This is also a really active part of development of the Python API right now, which is essentially to take all of the capability that you already have at your disposal in Player and give you programmatic control over that on a frame by frame basis, while also being able to orchestrate actually showing the visualization in the same way as orchestrating the simulation itself. But this is a really good introductory example of how to customize the visualization. And I should point out that every time this call to visualize is made, another frame is created. And the object that's returned is a reference to the frame that's created such that you can control and customize every frame that you create when calling visualize. And there's no coupling between the customization of any two visualization frames, with the exception that they all have the same underlying simulation data. So all frames will show the same simulation data, but how you customize the visualization, you know, whether it be the location where you are, say, looking, or what data you actually display, whether it's a diffusion field or the cells, all of that is on a frame by frame basis. And it's all done through interacting with objects that are returned when calling visualize. Okay, that's a crash course overview. I'd like to continue on and hopefully get to a point where we can actually do some interactive steering by developing our own widgets. So we are gonna make these cells move in an organized way, albeit a very naive way. We're gonna essentially tell cells to move either to the left or to the right in our simulation based on what type of cell they are. And we're going to do so by adding one more PyCore specs object, which is the external potential plugin. So let's move up a little bit. Actually, let's just for the sake of performance, let's do what's called a restart on our kernel. This will purge all of the simulation data from memory just to make sure that we don't have a bunch of junk making our Jupyter notebook execute slowly. So before we start, go to the menu bar, go to kernel, and restart kernel and clear outputs of all cells. And then restart. It should just take us back to our Jupyter notebook, but in an unexecuted state. for your reference, just to make sure, here's a copy of the last cell we were just working in as defined in my notebook. Okay, let's go up a little bit back to where we were specifying PyCore specs objects. None of this is order specific to the extent that all of these PyCore specs objects can be instantiated in any particular order. They can even be added in this list when registering. It's totally declarative, no specificity in terms of order. It's just important that what we instantiate for this additional plugin ends up going in our call to register specs. So let's create another cell. I'm going to do so at the very end of all of my PyCore specs instances. You can do so anywhere before calling register specs. We're going to get the external potential from PyCore specs. So from cc3d.core.pycore specs, import external potential plugin.
TJ. Oops.
Yes.
I might be. Can you hear me okay without an echo now?
Yes.
The TA couldn't solve it, so I'm just gonna ask it. Do you know when a kernel dies, quote unquote dies, and then automatically restarts, what's happening? Because it doesn't show any error in the code.
Yeah, it's a tough one. It could be a couple of different reasons. The most obvious one being that there's some issue with your binaries. You haven't had any issues with Player or Twedit?
No.
What operating system are you on?
Brand new computer. It's a Windows 11.
Okay.
HP Pavilion.
It's hard to tell you exactly just based on this information. I can, in the very least, I could maybe connect with you in a breakout session right after we're done and see if I can help you resolve it. Is that okay?
Sounds good. All right. Thanks.
Right. Well, appreciate your patience. Thank you. Okay, external potential plugin. So we've imported it. We're going to add the external potential plugin to make ourselves move in some organized way, even if it's an artificial one that we're going to control just for the purposes of demonstration. Let's start by instantiating this external potential plugin. I'm going to call it external potential specs and instantiate it and pass no arguments. This is just a shell. And then we'll populate it with some specification for each of our two cell types. And what we will say is that our cells of type 1 will move to the right and our cells of type 2 will move to the left. That's what we want to accomplish here. Now we can add parameters per cell type using the method param_new. Just like with the context specs, volume plugin, and as you get into the PyCore specs more, you'll find that this pattern is pretty common across various PyCore specs classes. Here, we will first tell external potential plugin which cell type. You can write this explicitly if you just want to say type 1, or if you like to code generically, like me, I'm going to refer to the first element of my list of cell types. So that's type 1, and I want my cells of type 1 to move to the right. So I will say x equals -10. Param_new, so the external potential has the optional keyword arguments of x, y, and z. If you don't specify any of these, then the value will be 0. So here I'm saying that the parameter along the x direction for cells of type 1 is -10. That'll make them move in the positive X direction. And we'll accomplish something similar for our cells of type 2. Make them move to the left by saying X equals 10. Again, here, if you prefer to just write this explicitly, you can also say type 2. I'm just referring to elements of the cell types list that I defined previously. Okay, I'll put this in the chat. And our last step is to add this PyCore specs object to all of the previous PyCore specs instances that we had registered. We go down to our call to register specs and just add this external potential plugin instance to the call to register specs. If you're following along with me, here's an updated version of my simulation startup code. And let's run it. So run all cells. Give Compucell a second to think. Now we're back where we were before we started this bit of coding, and we should find when we click run simulation, you should now see cells of type 1, which are blue, fighting their way to the right, and cells of type 2, which are the green cells, at least in my case, fighting their way to the left. Now, if you run this for long enough, what you will find over time is that this causes something like a sorting behavior, which is kind of interesting, and that the system is most efficient when cells moving in a particular direction all group together, so that it's much easier for them to move in the directions that they're trying to accomplish. It takes a little while for that to occur, and we're not going to sit and watch simulations run on my screen all day, but it's an interesting simulation to play with. I think that we're about out of time. The rest of the content that's prepared for this module is really to create a slider to be able to adjust the parameters that govern which direction cells of different types move. The example actually builds these widgets not out of anything that's predefined in Compucell, but it's a full integration of this Compucell simulation with third-party Python modules that are publicly available. And so I'll say that the materials that we've gone through and that have been prepared for this module, like other modules, will be available in the shared drive, and the rest of the material walks through the process of setting up something like a custom widget to be able to control this simulation. And I would encourage you, if you're really interested in diving further into the capabilities that are provided through the Python API, complete the rest of the module, walk through the example of setting up a widget to actually manipulate the model parameters as the simulation executes. I think with that, James, I can turn it back over to you.
Okay, well, there's time for questions, comments.
Well, I have one question that I actually posted on the chat, but honestly, my English is not very good, so maybe I wasn't able to explain myself. I I used to have a different import. So instead of using the import that was explained by TJ, I was using one that goes cc3d.core.sim service with not capital letters, so small letters. Import service underscore cc3d, and then the code, instead of being CC3D Sim Service with capital S in Sim and capital S in Service, the code that I was using was service underscore CC3D. And I was wondering if this import and if this code would work the same as just shown by TJ, or if they work differently.
Yeah, this is a great question. So the features that you're describing are certainly part of the Python API for sure. That service CC3D and all of that is the feature set to allow you to execute multiple CC3D Sim Service instances simultaneously. This is described in the documentation, and it was neglected today, mostly because it gets really complicated really quickly. But you have essentially discovered the feature set that lets you orchestrate multiple CC3D simulations simultaneously and concurrently, such that it's possible to even develop a simulation with multiple simulations. You can take a specification for a simulation of one particular tissue and a second simulation and execute them at the same time, and even connect them such that they share information and even affect each other's states. That's all through the features that you're describing. I think it's still true that those features will only execute in a Python script. If you ran into issues using that in the Jupyter notebook, I believe it's true that those features still will not work in a Jupyter notebook. But otherwise, they're totally valid, and everything that we've discussed today is true for those features as well. They are just intended for developing simulations of like multiple simulations at the same time.
Okay, cool. Thank you very much for clearing this for me. And
Yeah.
also, I had another question. Is there a specific method or function that we should use in order to export the data from the simulation that we're running? So for example, the simulation that you have here, if we wanted to export the position, an ID, and type of each of the cells that are that we are visualizing, is there a specific method that we should use in order to export it into like a CSV format?
Yeah, that's another great question. And to some extent, it really depends on how you've built your simulation. For a single simulation, as we've built here, you at any time can pull any data out of CC3D as you please, either directly through accessing like CC3D's actual data directly, or you can also use everything that you've already worked with through steppables. So you have a lot of flexibility when using a single instance of CC3D Sim Service. I'll say that for the other feature set that you described, or that you discovered with Service CC3D, that feature set gets a little more complicated when doing multiple simulations simultaneously. And for the most part, I'll say it's described in the documentation, and I would also be happy to discuss it separately, but it can get pretty complicated, and I'm not sure I can adequately explain it in under a minute or so. I'll say that it is definitely possible to get data in and out of a simulation, even through those features where multiple CC3D simulations are executing simultaneously.
Okay, could you please
Okay.
maybe share the documentation?
Yes.
Thank you really very much.
Right, thank you.
So I think Henry had a question, and then Omar, and then Gopal.
Uh, yeah, hi. Thanks for the talk. You mentioned in the uh, the motivation of using the Python API that one of the greatest things about it is that it can do stuff like optimization parameters or multiple simulations. Do you know how where we can find out how to do those things, or can you direct us to like what the code would look like?
Yeah, great question. And so at least for the two examples that you mentioned, we currently have an example of each of those applications in the distribution. I can grab the link and put it in the chat here in a moment. But at least for the case of optimization, it's certainly straightforward. Once you've gotten to this point where you can execute, like actually launch and orchestrate a simulation, it's fairly straightforward from here to construct something like a cost function for minimization. In which case then integration with SciPy or LMFit or otherwise, is mostly routine. For the concurrent simulation, that one's a little more complicated. And we do have one very simple example of doing this. Again, I'll grab the link here momentarily and put it in the chat. You should be able to execute both of those examples as is just by downloading them from the repository.
Thank you.
I've got a couple questions. Oh, people have their hands raised. I'll raise mine too.
Hi, Sharon.
I don't want to jump ahead of the people who raise their hands. I'll raise mine and go in order.
Sorry, James, I know you listed who all was up, but I've forgotten the list.
The next is Omar. Omar.
Yeah, thank you. I tried to launch the Jupyter notebook, but I have external Anaconda installation. So the TA that helped me told me that this is interrupting the internal Miniconda for CC3D. But I was told that there is a way that I can install CC3D in my own Anaconda installation. So is there like written documentation for that in the or how can I do it?
There is. Would it be easier if I just gave you the command directly in the chat?
Okay.
Okay, I can,
Good.
I can just add
Thank
it
you.
there right now for your reference.
Okay, Gopal.
Hi, Keshav. So I had a question regarding parallelization of solving diffusion fields. So like I went through the documentation, it mentions about using OpenCL integration for using GPU for the solver, but it didn't work quite well for me. So is there a third-party module which I can integrate with this Python API to parallelize it so that I just want to reduce the runtime required for each simulation in the project which I'm working.
Sure. I mean, it's certainly possible to use say diffusion fields that you solve through like the CUDA Python module or comparable. I mean, in general, Compucell has extra fields that can be created that you can essentially copy your own field solutions into. Of course, it's also possible to just maintain your own diffusion solutions, that Compucell really doesn't know anything about. In which case, in say something like a custom steppable, you can integrate that data into your Compucell model however you please. So you certainly don't have to rely on Compucell's diffusion solvers for most things. There are some things that I think are probably not straightforward to accomplish, but in general, you can maintain NumPy arrays or whatever else that Compucell really could care less about, and it doesn't even know about, that you could say solve with CUDA or otherwise. As far as the build with OpenCL, I mean, that I think probably I can't be very helpful with that, at least at the moment. That's also, I'll say, a very new feature set, reviving OpenCL support. So there is always the chance that there's just a bug that we're unaware of. If anything, I would suggest maybe reaching out through the GitHub repository by filing an issue, and that will get you connected to me and the other Compucell developers. That's probably the best way to address that.
Okay, sounds good. Thank you.
Thank you.
Excuse me, Jaren, are you here? So me and
Yes.
Jaren were okay. I discovered what's wrong. Me and Jaren, we weren't able to move the simulation screen, like it was frozen, and the run simulation button did not work. So now I've tried to just cut the file from my drive to my desktop screen. So and then I try to run it again. Then it works. I think there's a problem with the folder, maybe the path to the folder on the drive.
Yeah, I mean, that's certainly possible. In the very least, there are always potential issues for, administrative privilege. You may have just
Wait, what did you do?
I've just cut and copy the IPy, not the program, to the desktop screen or any other screen, not in a very long path, maybe. Just in the computer screen. And then try to open it and run all again, the kernel.
My turn?
Sharon, I think you're up.
Okay. Maybe I missed it, but I don't think you said anything about how to add steppables. Is there a way to get the standard default steppables, modify them, and register them in a similar way?
Yeah, it's a great question. So all of the built-in steppables, like the diffusion solvers, box watcher, and some things that maybe don't get as much attention in the workshop. So all of those are available in the PyCore specs and are registered in the same way that we covered today.
And then you can
Custom-
just,
Yeah,
I
and
suppose
there-
you get a file which you can then edit and then pass a reference to it back, a reference to the function, I guess, when you register. Like, what if I want to modify my steppable or write my own?
yeah, for custom steppables that you define yourself, there is an analogous call to register specs that we did not get to, and that is register steppable.
Okay.
And
And
you just-
the typical stuff that we do in these workshops is we start off with one of the basic steppables, like, mitosis or whatever, but then we go modify the code. So how did you do that? Does
Yeah.
that count as a custom or?
Yes. Yeah.
Oh, okay.
Anything that's available in the binaries, like a volume plugin or the diffusion solver FE, anything that you can't customize in Python, those are all in the PyCore specs. But any steppable that you define or customize in Python, you can also register with your CC3D Sim Service instance by instantiating it and passing it to register steppable.
But can you get the template that we normally get by saying like, give me the mitosis steppable?
Yep, it's all the same. You can take the steppables that you have defined throughout the week so far and use them through this interface, and they will function literally the exact same way.
Okay.
Yeah, just
What-
inside your service instance instead.
And then I'm just curious, there are the code snippets from Twedit available? I'm just looking
No. No, what is available though is complete Python API docs.
Okay. You said you could do anything that Twedit could do.
Yeah,
I
well,
suspect that might not be one of them.
generating code for you, you can rely on ChatGPT.
Ah. Yeah, right.
Although it doesn't know about any of this stuff yet. But no, I mean, there are no features to code for you currently in a pure Python script or Jupyter notebook, that's for sure. So yeah, one thing Twedit can do for you that a Jupyter notebook currently can't is automate code building for you. Yeah. So
And can
this
I
is-
do this in PyCharm instead of Jupyter?
Oh yeah.
Good.
VS Code, yeah, PyCharm, all of the IDEs. I mean, this really, at the end of the day, this is bringing Compucell to basic Python programming level. I mean, through this API, you are controlling Compucell very similarly to how Player orchestrates Compucell.
Cool, thanks. Good talk.
Yeah, and there's one comment there in the chat that I haven't addressed, but it's important. I'll note that there are features in the Python API to convert to and from CC3D ML and Python objects. So if you have existing CC3D ML that you want to use in Python, there is a function in PyCore specs that will create Python objects from your CC3D ML or vice versa. So everything that you've defined so far this week is not it's not a loss in terms of migrating to the Python API. You can just pass a path to your CC3D ML and create these objects automatically from that specification.
I don't know how long would it take to demo that? Could you show just the call for it to a
Sure, I just have to look it up.
Okay. That might be important, I think. And was there another question? Katrine, did you have a question?
It was a question which came to my mind because reproducibility is a big thing today. And when we now use a kernel, let's say 3.1, and in 10 years, someone uses a kernel 6.7 or something like that, so the results may be different. Does this have any impact, or can we just store the kernel in the code?
Like the IPy kernel?
Yes, this is just something I heard, that the kernel may play a role in the simulation.
So it certainly wouldn't affect Compucell, because Compucell is executed in C++ binaries. So the only thing that could potentially be affected is the Python layer. But even in that case, no, there's no effect, because these Python API features are actually really just thin wraps over manipulating the same data that's created from the CC3D ML. And that CC3D ML generated data is also done in the binaries. So, no, there's maybe effects on integrated features. For example, this little convenience feature, this is built from IPy widgets, which is specified in Python. And so maybe there are effects with those sorts of things, but certainly not with the actual simulation data, because Compucell is C++.
Yeah. Okay. Thank you.
That's great. That's a great question. Okay, so the request to very quickly demo generating PyCore specs from CC3D ML. So I don't have how to do it. So there's a function in PyCore specs. So from cc3d.core.pycore specs import from file. Make sure I've written that correctly. Yeah, from file. And what you will find is that if you pass the absolute path to a CC3D ML file, and it's CC3D ML file path. So that has the path to my CC3D ML. This will return a list of PyCore specs instances that can be generated from your CC3D ML. So it's actually possible to, and what's returned is a list. So it's actually possible to do this. Call register specs and then just from file and then a path to your ML. Since this returns a list of specs objects, this is the intended pattern. So that if you want to use previously defined CC3D ML, but you want to use it directly in the Python API, you can do this exactly as written. It's also possible to generate CC3D ML from a list of PyCore specs on the topic of things like reproducibility. And I have to look up the name of that one too. I don't remember it off the top of my head. Suffice it to say for now that it's there and it's documented, and I can't recall off the top of my head. But yeah, interoperability between the CC3D ML and Python API is actually a pretty big priority for this feature set, in terms of preserving all of the work that's been done prior to developing these features. Because the goal here is not to eliminate the ML, the CC3D ML or play or any of that. It's really intended to have a complementary set of features to be able to use Compucell in other ways. And the path that can be passed to from file can be either the CC3D project file or just the XML. Either one will work. It'll adapt.
Okay, thank you so much, TJ.
Thanks, James. Thank you, everyone.
If you could upload the slides and the notebooks, that would be great. I think people are really eager to see that.
Will do. I also think some people some links to some available demos and notebooks